Physics 2212, Lab 4, Magnetic Braking with Faraday by Swam Sanket Kumar Trivedi. Introduction. Purpose. The purpose of this lab is to show how a falling bar magnet induces current in an aluminum foil tube and how those currents create a magnetic force that slows the magnet's fall, and compare the results with a computational model generated in GlowScript, where the system in this case is the bar magnet and aluminum tube and the surroundings is everything else. The fundamental principles used is Faraday's law, which states that a charging magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux, with the induced voltage opposing the charge of flux, which is Lenz's law. Biot-Savart's law, which states that a steady current produces a magnetic field around it, with the strength depending on the current and distance from the current carrying segment. Newton's law, where the second law states that the net external force equals the change in momentum of a system over time, and the third law, which states that for every action force there is an equal and opposite reaction force. The preview of the main results include the experimental time as 1.254 seconds and the computational time as 0.861 seconds. These are the main physics ideas which I had mentioned on the previous slide, and the formulas that I should be using throughout the experiment in order to obtain the results I have. So that's Faraday's law, Biot-Savart's law, and Newton's second law, and the formulas have been described. Throughout this experiment, there were some procedures and an assumption. The procedure was that we drop an aluminium foil through a tube, and through this we are able to find out what we do, and that's exactly what happened. As you saw, the aluminium fell through the tube. So some assumptions that were included were that air resistance is negligible, the bar magnet is modeled as a magnetic dipole, and the only force acting on the system are the magnetic and gravitational. So that means in this case we neglect kinetic. This was the experimental data that I obtained. So in the 5 trials I did, this was the times that I obtained for each. These are the exact dimensions of the tube and the magnet's properties, and the average time that it took to complete the experiment was 1.254, which I calculated by adding the seconds and dividing it by 5. Computational model and the initial conditions. These were the initial conditions I kept for my GlowScript code, and over here I was able to check the physical constants. I was able to keep the geometry of the tube that I had found, the properties of the magnet, and then I kept it into the formulas I had told before and described the main physics formulas, and then I calculated it. This is a more detailed explanation of the forces. It's a picture of the code I had done, and basically the parts and each step that it took in order to calculate it, in order to calculate the time taken in the GlowScript model. So this was the data I obtained. You can see that there's a small, it dips, flattens out, and then dips again. So the orange part is basically when F gravity is greater than F mag, and in the part where it's straight, it means the F gravity is equals to the F mag. And the tube created, this was the tube that was created, the model that it simulated, and the time in the tube that it took according to the simulation was 0.861 seconds. We were told to answer some questions. So which color indicates clockwise versus counterclockwise current? So according to Lenz's law, the red trace represents counterclockwise currents and the blue trace represents clockwise. So what happens if a magnet is flipped? The magnet still falls through the tube, but the induced currents reverse direction. How does the measurement fall time compare to the simulated time? The simulation predicts a slightly shorter transit time. Adding air resistance and minimizing timing errors improves the match. And what does the velocity profile reveal about the forces of the magnet? Well, gravity exceeds the magnetic braking force at the tube's entry-exit, but with the tube they balance, yielding at a constant terminal speed. Some potential errors include measurements such as the stopwatch was not precisely started stopped, which is basically a human error, and inaccuracy of magnetic dipole moment. Another is friction, where the magnet might hit the side of the tube, or air resistance that acts as the aluminium falls down. What if the tube's resistivity approaches zero? How would the magnet's motion change? So using Ohm's law, V is equals to IR, lower resistance allows larger induced currents, which produces a stronger opposing magnetic field, so the magnet would slow down even more. And what if slots were cut along the tube? How would this alter the ring's currents model? So including slots breaks the continuous current loops, reducing the number of strength of eddy currents, and the weaker opposing field would let the magnet fall faster. Thank you.